So hello and welcome everybody to today's weather briefing. It's just 11 o'clock. I can hear the church bells ringing over here in Austria. My name is Liliane Hofer and I'm leading the weather briefing today. I'm working at the National Weather Service in Austria at ZAMK, and my office is located over here in Salzburg, as you can see. And now, just for introducing ourselves, I would like you to pick your star and place it to the location you're at the moment. Okay, very nice. So people from all over Europe nearly, mainly from Eastern Europe, but also from Spain. I think I've read in the text chat box that we have also some colleagues from Wales here. Okay, so thank you everybody for your star. And my weather briefing today will be divided into two parts. First, the analyzing part and then the forecasting part. And it's a kind of special thunderstorm edition, I can also say that much. And before I start with the analyzing part, I would like you to tell me whether you have observed some heavy thunderstorms or even some hail during the last week. And if yes, please put your star to the location where you observed thunder and lightning or even hail, some severe gusts. Okay. Okay, 2, 3, 4. I also saw some thunderstorm over here in Austria. Yeah. Okay, thank you very much. And now we will just jump to the analyzing part, jump to last Monday, the 9th of June, so-called Whit Monday. It was a holiday over here in Austria, which was quite nice. And here you can see the infrared 10.8 image taken from ePort and the 500 hectopascal geopotential height. Very interesting weather pattern. We have this distinct low over the Atlantic Ocean and this ridge over great parts of Central Europe, bringing nice and summery weather conditions. And these two systems, they provoke a southerly to southeasterly streaming pattern, bringing really warm, one can really say even hot air masses from the North African region to France, the Benelux, Germany, and even to Poland. And this air mass was not only characterized by really high temperatures up to 34 degrees, but also by really steep lapse rates in the radio soundings. And that means really unstable conditions, really thundery conditions. And I mean, it's 6 UTC, but you can already see some thunderstorms developing over here. And the reason why they are developing mainly in this region, we will see on the next slide. Here we have again 6 UTC on Whit Monday, but now we see the equivalent thickness instead of the geopotential height. And you can see over here this frontal boundary, which is quite stationary, which shows also some wave developments over here and over there. And yes, this frontal boundary, this may lead to lifting and therefore to convection. Before we now continue, I would like to make a small excursus. I would like to show you today the Global Instability Index, the GII. And the GII is a kind of a combination of model data and satellite observations. And it's a satellite-derived parameter for describing the layer stability of the atmosphere. And normally, the information about the stability of a layer is taken from temperature and humidity soundings from radiosondes. But as you know, radiosondes are only available at certain places and at certain times. And so the big advantage with satellite-derived data is that it's available more often and over a larger area. And so we will take a closer look how this is computed. As I said, it's a combination of model and satellite data. And the first estimation for the GII is a vertical forecast profile. So a temperature and humidity profile. The source for the GII you can find at ePort is ECMWF. And this forecast profile is then taken and serves as input to a radiative transfer model. You probably have heard of it. It's called RTTOF. And the output of this model is then brightness temperatures. So you take the model data, put it into the radiative transfer model, and then you get brightness temperatures. The same brightness temperatures as if you would have taken satellite observations. And that leads us to the satellite input. So you need something to compare to the model output. That means temperature and humidity information. And so we can say we can't use the visible channels because they are solar channels. So we can't use those 4 channels. The infrared 3.9 is kind of a special case because it's contaminated with the solar component during daytime, so we can't use this one. Remaining are now these 7 thermal channels, but the infrared 9.7 is the so-called ozone channel, so it's mainly responsive for ozone in the upper troposphere, so it's no use for this vertical profile of the atmosphere. So remaining are those 6 thermal channels. So we take the brightness temperatures and radiances from this and compare it to the model data. Okay, if there are a big difference between the computed brightness temperatures and the measured brightness temperatures, the profile is adjusted. It's changed in the direction of the observed brightness temperature. And this process is iterated as long as the difference is big. In the end, we have a slightly adjusted profile, and in most of the cases, in about 50% of the cases, the first profile, that means the model profile, is good enough. So there are no big differences between the model brightness temperatures and the observed brightness temperatures. For the rest, for the other 50%, only 1, rarely 2 iterations are needed, and then the vertical profile is good enough. This means that the computed indices are close to the forecast, close to the model data, but with the help of satellite observations, local extremes and or gradients are changed. So you have kind of a benefit to just using the model data. Now, which indices are available? I mean, what do you need for thunderstorm forecasting? Probably all know these indices. We have the lifted index, which is a sign for the stability of the 500 hectopascal layer. As you take the temperature of 500 hectopascal and then the temperature of a parcel that is lifted to 500 hectopascal. Also available is the K-index. The K-index has the big advantage that also some humidity data is used. I mean, some dew points. And then we have the total precipitable water. And those 2 indices that are highlighted, that means the lifted index and the total precipitable water, those 2 indices are also available at ePort, and therefore we will concentrate on those 2 indices. But before we will take a closer look at images, just a short summary of the advantages of using GII. I've already mentioned it. You have an increased spatial and temporal resolution in comparison to radiosondes. So MSG is available 3 kilometers nadir and every 15 minutes. And you have more information than by just using model data. The one big disadvantage is that you can only compute GII data over cloud-free areas, because if you can't see the surface and lower layers, you cannot obtain any information about the stability. Okay, but let's take a look at the images. It's still with Monday, the 9th June, 6 UTC, and we have the infrared 10.8 overlaid with the GII, and especially, I mean, here, the lifted index. You see here the color scale, so that means brownish colors show positive values, that means stable conditions, and these colors up here, the more negative, the more unstable the conditions are, at least in the layer of about 500 hectopascal. So we see unstable conditions mainly in this area over here, so in a really large area. But I would say we concentrate on the western parts of Europe, means in this area. We can already see some cloudy areas over here. That means we can't see any GII indices, but we see some yellowish to green colors over here, which means lifted index values up to -8 Kelvin, which is quite unstable. What about the total precipitable water? It's really a difficult word to say, at least for me. Take a close look at the color scale, because red means really low values, and when it comes to green and blue, it's really high values of TPW. And in this area, we can see values up to, I don't know, 35, probably even 40 millimeters of total precipitable water. That means if a thunderstorm is forming there, you can expect rain rates in that scale. Okay, no surprise, in the Alps it's more or less dry, and we also have quite moist conditions over here. So 6 hours later, only 6 hours later, we can see that the GII, again the lifted index here, has really decreased. So we see red values in this area, which means lifted index up to -12. And if the lifted index is decreasing in time, that means that the instability is increasing. Let's take a closer look at the TPW. Yes, there hasn't changed that much. What we can see is that the convection is developing more over here. We see some quite pronounced convection here over Turkey, Romania. But as I said before, we will concentrate on this area in front of the frontal boundary. Okay, the infrared 10.8 image is probably not the best option for monitoring convection. A better option is surely the HRV RGB, because you have on the one hand the high resolution information about cloud structure and cloud development due to the high resolution visible channel that is used on the two color beams, and you have temperature information due to the infrared 10.8 channel. So you can estimate the cloud height. So it's a really perfect tool for monitoring convection, and you can see those CBs even more pronounced over here in France, over here in the Netherlands or Bulgaria. And you can even see the anvils, at least a little bit. And now let's see what happened further. Therefore, I have this loop. Please show me a green sign, this green, this one, if you can see the loop, if it's working. Okay, I can see the first yeses. Okay, perfect. So what you can see is a loop from 16 UTC to till the evening, till sunrise. Again, the HRV RGB, and you can see this CB is really rapidly growing. It's more or less MCS now, and it's really impressive. I hope everybody has seen the loop. So I will continue with the next slide. Okay, 4 people haven't seen it, so I'll give you, 6 people. I will give you some more seconds. Hopefully you can see it then. Okay, I will now continue. I mean, the loop shows some HRV RGB images. But what I do in the next slide is I pick out two images, and this time I'm not using the HRV RGB, but the so-called sandwich product. The sandwich product is a satellite image consisting of two layers. The background layer is the high-resolution visible channel, and on top of it you have the infrared 10.8 image, but the color-enhanced image. And the product you can see here, it's called the sandwich product, and this is also a really good product for monitoring convection because you get kind of a 3D structure of the convective cell. As you can see over here, you see really pronounced this overshooting top. See it really nicely. Also over here you can see something, and you get some temperature information. So it gets kind of blackish over here, and blackish means temperatures up to minus 70 degrees Celsius. So that's really, really cold. It's really a high potential for hail. And what more can you say? Overshooting tops are always connected to severe weather events. So if you see overshooting tops, they can be a sign for severe wind gusts, for hail. And so this product is really good for nowcasting and for monitoring severe convective cells or mesoscale convective systems as this one. So that's 1715 UTC, and the cell is this big now, covers nearly the whole Belgium, and an hour later it's even bigger. We can again see very pronounced the overshooting tops over here. What more do we see? That in the southwesterly to southerly stream, more convective cells are developing just behind this MCS. And you see it's 1815 UTC, so sun is setting and the cell is still growing. I want you to take two locations in mind. So we have here, somewhere here, I think should be a city called Landgraf, and somewhere here should be Jülich, because I have later on I will show you some images from these locations. But before, I would like to show you the ESTOFEX, not so much the forecast, but more the verification. I think you all know ESTOFEX. The ESTOFEX overlay is also available at ePort, and you see they have forecasted a level 3 warning for this area. And what you can furthermore see are those weather reports. Mainly these yellow signs, and yellow means severe wind gusts. We also have some green triangles. They are a sign for large hail, and also a heavy rain observation over here. So there was a lot going on. I mean, you can you can see it on the satellite images that it was a really monster cell. And now we have talked a lot about radio soundings, about the indices you can get from them, and here is one. It's from Bergen, which is in northern Germany, just south of Hamburg. And as I've told you in the introduction, the air masses that were evacuated from North Africa were characterized by really steep lapse rates, as you can see probably here. And this provides a large CAPE values. In this QT diagram, this area resembles the CAPE, and we have CAPE up to 1600 joule per kilogram Kelvin. What more can we see? It's really moist in the lower layers. I hope you can see the wind barbs over here, the wind shear. We have 40 knots and 500 hectopascal height, so it's not too bad either. And if we compare now the GII values to these values, okay, it's 6 hours later, now it's 18 UTC, and we've taken a closer look at the GII from 12 UTC, but nonetheless, I would like to compare it. We have precipitable water, that means TBW of 35. That's really comparable to the GII value, and the lifted index shows values up to -5 degrees. It's a little bit lower than the TI values, but remember it's 6 hours later, so values might not be too bad. Now some lightning data. This is 12-hourly lightning data, so it's from Monday midday to Monday or Tuesday midnight. And you can see, I think this should be 300 kilometers wide, so the width of this MCS, the lightning path, it's really incredible. It was really a heavy thunderstorm. And what more can you see? The color is a sign for the time. So I think the yellow color are the latest lightnings, whereas the red color indicates that the lightnings are older or were earlier detected. And you can see that this is the path of one cell, but another cell was there before, and the same is true for this region. So numerous thundercells developed on this Monday. Okay, as I've promised you before, here's some images. Remember Landgraaf, it's a city in the southern parts of the Netherlands. And on this Monday, a music festival, so-called Pinkpop, was going on. And the squall line, this thunderstorm was approaching Pinkpop. And the organizers have not canceled the event, but just interrupted it. And they were pretty lucky because there were no severe injuries or anything like that. And the crowd was really tolerant and kept quite cool. And so nothing happened. But yeah, I think it's the horror for every organizer if a system like this is approaching a music festival. And this picture was taken at Jülich. It's in North Rhine-Westphalia. It's, I think, just 20, 30 kilometers east of the location where Pinkpop has taken place. And yeah, you can see this quite organized storm structure and this really incredible image. So yeah, I mean, if I would have been at that point, I think I would have started running at that site, although it's kind of beautiful at the same time. So yes, and I've shown you that there were some more thunder cells developing over France, and this is an image that was taken southeast of Paris, and you can see this hailstone. It's yeah, quite unbelievable. So that was last Monday, so just a week before, and now I would like to jump to yesterday. 16th of June, and it looks like, if you compare this situation to the situation a week before, it looks like the ridge and the low have changed places, because now the high pressure system, the ridge is over the Atlantic and the trough is over Central Europe. What more can we see in this image? We can see some frontal system over here that's kind of blocked by the ridge, and we see some frontal cloudiness over here, but let's look at it with the help of the equivalent thickness. So I would like to concentrate on the thundery region over here. What can we see? There seems to be a kind of frontal pattern like this with occlusion, cold front, and warm front. And in the really warm air masses, we have here values up to 240 Kelvin. First thunderstorms are developing. I've chosen here the water vapor satellite image just because the contrast is a little bit better than using the infrared image. I mean, you can see the cold thunderstorms more pronounced in this image. Okay, as we have made as we have seen that the GRI is a really powerful or at least helpful tool, I would like to show it to you again for this case. So already at 6 UTC, we can see unstable conditions over here, kind of in front of the trough. Lifted index values up to -8 Kelvin. And you can see there's already something going on, but there's probably still potential for more, and some outflow of these cells may trigger some new cells. And so if you're a forecaster and you come to work in the morning and you see this image, so you clearly know at which areas you should concentrate on. So 6 hours later, again, we will use the HRV RGB as it's one of the best tools for monitoring convection. You can see quite a lot of cumulus clouds over continental Europe, but just small clouds, so no big systems, probably just some showers. And you can see some more pronounced convection over Turkey, just as the GII indicated at 6 UTC, and several convective systems over here, over the Mediterranean area, over southeastern Europe. But the problem here with the HRV RGB is that you see lots of cells over there, but you can't really indicate the several cells. So for this purpose, we can take another satellite image, handmade sandwich product, so to say. You can find the visible 0.6 channel at ePort and the enhanced infrared. And if you choose both images, you get this one. And there you get temperature information of the cells. So you see the tops reach up to, let's say, 215 kelvins, and you can isolate the storm tops. And also of good use is the so-called severe storms RGB. It's a kind of a complicated RGB because it uses 6 different satellite channels. I haven't written the recipe over there, but probably of notice that it also uses the visible channel, so it's only available during daytime. And the big advantage of the severe storms RGB is that convection can be easily monitored, and CBs containing small or large ice particles can be identified. If you take a closer look over here, so convective cells appear in shades of red and yellow colors, and yellow colors indicate small ice particles, so you get some microphysical information. And small ice particle means that there's a large updraft, so the particles don't have time to grow together. And so yellow means highest updrafts, and so high potential for severe weather conditions. So this is also a really helpful tool for monitoring convection, forecasting convection. And so when we're talking about forecasting convection, let's take again a closer look at the GII, this time at 12 UTC, so 6 hours later. What can we see? So here over southeastern Europe, over the Mediterranean area, there are too many clouds, so you can't get any more information from the satellite data about stability or instability. But over the Iberian Peninsula, the instability has increased as the GII has decreased. Also over Northern Africa and over Turkey, we also have some red colors over there. So as a forecaster, what would I do at that moment? Where would I concentrate on? I mean, we see that there's already some convection going on over Turkey, so there might be some further developments. It's still unstable. And I would really concentrate on this area over here. So Northern Africa and Spain, there's not that much convection going on, so there can be some convective developments there. And if we take a closer look how the situation changed within 6 hours, we can really see some thunder cells over Spain with temperatures up to 220 Kelvin, And yeah, over Turkey, not so much has developed, but you know that 6 hours later, that doesn't mean that, I don't know, at 16 UTC there were some big cells. But yeah, what we can say is that GII is a really helpful tool. It can help you probably a little bit more than just radio soundings because it's available at a bigger spatial and temporal resolution. And if there are no clouds, it can really be a big help. So let's come to the conclusion. When forecasting thunderstorms, when forecasting convection, you should first check the ingredients. That means moisture, instability, and lift, and the satellite images. So you see, are there already some cells? Is there something developing? And then for issuing a warning or for issuing a forecast, you can always use satellite-derived parameters like, for example, the GII I've shown to you with the lifted index, the K-index, and the TPW. And satellite images like the HRV RGB, the sandwich product, or the CV Storms RGB I've shown in the last slides. They can really help nowcasting such situations, and they can really help you to issue warnings or things like that. So I think if you have a really, I don't know, thundery condition going on, then you can use lots of satellite data, and it helps you to improve your forecast. And that's it for today's weather briefing. The next weather briefing will be on the 10th of July at 9 UTC. It will be led by Alessandro and by Andreas, and the link for registering should be soon available at our website. And that's it from my side. Thank you for your attention, and I hope I will see you next time around.